So, my name is Vitor Oliveira. I've been working with group replication and optimizing group replication and on performance, basically, for the last times. So, what I'll be doing today is presenting some ways that you can, some options and some ways that you can optimize group replication for performance. Okay. So, I'll skip this. You have seen it, and this will also go. So, I'll try to explain better than showing benchmarks and everything. And we all know that benchmarks have a purpose, have many purposes, but actually, for a production user, they mean very little because they need to run it with their workload, and they are just metrics that you can use to try to understand what's happening. But the real benchmark is the workload that we need. So instead of that, I'll try to explain how it works behind the scenes in some things that impact performance, so that then each person can check what the workload is doing. Okay, so let me start with this anatomy of group replication. So in group replication, we have basically two big parts. So we have the transaction, and after a transaction is prepared, so it executes and it's ready to on a node, and it's ready to be propagated. Group replication enters at this point where it's ready to commit, and then it gathers the right set information. Then it does what I call is a throttling point. So I'm going directly to these details because I think people here prefer this lower level things. Okay, so then we go to the details of delays if needed, and then we send the message out to ordering on group replication, as Alfredo was showing. Okay, then at this point the thread just waits. It just waits there for something to happen, and that something is going as the transactions going to the network, being ordered in agreement with all nodes, and then getting back to the certification on that same node. And this is what's happening here. Okay, so then once the certification result is in, then the thread can continue. And at that point, the certification is either positive or negative. So there is either a conflict or there's no conflict, and we can go on. And then we decide to commit or not. This is basically the main entry point for group replication. Which also means that if someone traces what's the application doing or something, why is group replication slow, this is not where you'll be seeing it much. Okay. Because it would just send it to the network and then wait for something to happen outside. The second part is this one, where indeed we have a loop that handles the data that gets in from the network, ordered, and at that point we receive the transactions, get them ordered, and we get a transaction one by one, and then decide to certify and then see, according to the state in each node, the GT executed in each node, and the information that comes on the right side from the network, we decided if they are compatible, that we can proceed with that transaction, or if you have to abort. This is deterministic because all the nodes receive the transaction in the same order, so the decision is the same on all nodes. This is what makes the multi-master system work. Okay, but there's here a split, which is if the transaction is local, we don't have to do anything else than, okay, saying fine, commit, and go on. But if the transaction is not local, and the certification is positive, we need to store that transaction to be applied. We don't execute the transaction immediately. We just reuse what's already available with asynchronous replication, which is a slave applier. We put it in the relay log, and then eventually it will apply. And this is the two main areas of group replication, which means also that we have these factors affecting our performance the most. Okay, so of course the obvious ones: network bandwidth and latency. Slower networks will be harder to deal, but particularly latency, very high latency, will make us drop performance. But this happens to everyone, so that's fine. You just have to adapt to that. And then the certification throughput also is an important factor, because The certification is a sequential process. We do it in a single thread that decides what happens to the transaction. It's not a light. It can do many transactions, but you will have to be careful with that because it may take longer, and then we start delaying the acknowledgements because of that particular thing. Okay. And then, of course, the remote applier. Once they get to the relay log, they depend on the same thing that replication depends, which is the throughput on the slave applier and the number of threads on slave applier that can actually perform the remote apply. Okay, so let's see what this means. This means that these points here are the main contention point. That one is not that much. It's a small point where we gather the right set information. It takes a bit, we hash it, but it's very light, not something very significant. But then we have this process. We have to send the message out. We have to reach an agreement and then wait on a certification on that side. Okay. So this is the main contention points on the certifier. We have to make sure that the certification itself is able to keep up with the pace we have, and we have to make sure that the transactions get to the relay log at a rate that is enough to not delay the system. This can also be an issue. And again, the applier. It's really good. So we have a few options. Here that allow us to control these things. Okay, some are not very controllable, but for instance, if we have high latency, of course we can put more transactions, and we need to extend more, be able to put more transactions in the system, and then they eventually arrive, and we hide the latency. We keep a high throughput at the cost of increasing the latency on transactions. But at the point where we intercept the transaction, we have the transaction prepared, all logs are there, but then it's very lightweight. So increasing this latency, you don't contend between threads a lot. So it's fine. If we increase the transactions, parallel transactions, it will behave rather well. Okay, but then if we can do something, which one is, okay, let's compress the bandwidth. We have a slower link, let's compress it and just send it. And take advantage of the fact that compression, compared to the network, can be at a high rate of compression, so we can mostly use the CPU to compensate the network limitations. We can also reduce, of course, the bin log itself and use a minimal so that the rows that we send are smaller. And then this is this one, which maybe I shouldn't put this here, okay? Because this is something for very low level. If we want to tune, in some situations, what happens is that we found this to be effective in some situations. So it's here because it may be useful. But this is very particular, which is if you have bursty situations where you have sent something, then you wait, then you send, then you wait. Sometimes the thread that's receiving the threads will go to sleep. Scheduling out this thread that makes the reception delays the entry of the same thread again. So if we can avoid this for just a bit, and sometimes we see a big throughput because it never sleeps, and this depends on the network. So fine, don't worry too much about this, but it may be handy in some situations. Okay. So the certifier throughput. We have to certify, and as I said, we have to write it to the relay log. This is done sequentially. We certify and put the transactions there. Actually, we tried a solution where we did this in parallel, but the benefit is not very big because in the end, you'll be limited by the throughput of the writing to disk. Okay, so in that, either you are able to handle that throughput, or you improve just a bit, but then you will still be limited by that throughput on disk. So take care of where you put your relay logs, and if they are indeed, the system is indeed capable of handling the throughput you want. Otherwise, if you may have nodes that delay the certification compared to other nodes, and that can be quite a delay if you don't take care. There's also another issue that may happen when you have multi-master nodes, write to multiple masters, which is if we try to send the same GTIDs, use the same, to use the GTIDs sequentially in two different nodes, we try to get from one node and then try to get from another. What this makes is the GTID executed sets will be very large because they are not able to compact. The GTID sets compact very well if they're continuous. And if you have two nodes and they are trying to send the same thing, they will be building larger GTID sets. And this is important for the certification process, okay? So if you use multi-master, please do not put this to 1, otherwise the performance will really drop as the certification itself, the certification info, will grow more than you need, actually. The consequence of this, which is not a big problem, I think, but it may in some situations, is that the GTIDs will not be contiguous. So you have the GTIDs from one node that will have an interval, the GTIDs from another node will have another interval. Then when those intervals are exhausted, they'll get another interval. So you have GTIDs in blocks when you write to multi-master, okay? But this is something that, by default, it's already 1 million, I think. So, but please don't put this to 1. And then we have the applier side, okay? The applier side, of course, we have to, if we want to use the parallel applier, we have to use the logical clock scheme, scheduler, and we have to have enough threads to handle the workload. Fine, it will depend on the system where you are running this, and if possible, use more than less. But after a point, it just doesn't pay to have more threads. And that point may be between 8 and 16, and depending if it's so really write intensive, 24, 32, but then we start having contention on the distribution also. So one good thing about group replication in the player is that we take advantage of the information that is used for certification to improve the parallelism on the slave. What this means is that we already decided which transactions are compatible or not between nodes. We know that from certification. So we also know which rows in the transaction are compatible between themselves. So we use in group application, you use that information to schedule the transactions on the slave player. Okay? And what this means is that we can ramp up much faster on the slave player using the right set information than using the binary group commit. Okay? Asynchronous replication, what uses is that it mostly groups the transactions that are in the same group commit. It says, okay, if they all committed together, it's because they were parallel on the server, and we use that information to run it in parallel on the slave. But if we have a very fast storage, very, very fast storage, and only a few threads, the group commit, without having some delays inserted, will be very small. Only a few transactions will commit together. And in that case, we'll have a little parallelism on the other side, on the slave player. If we use right set information here from group application, we can take advantage of this fact that we don't need the group commit to decide what needs to be parallel or not. So even with only a few threads, we can get already a lot of the throughput of the slave player. Okay, this is one of the benefits, and it's something that probably reduces lag in situation where we have lag right now with asynchronous application. Okay. So one other thing that's that we decided that, of course, Galera also has it, but here it's important for us to keep the nodes mostly, and I mean mostly, close, but not exactly in sync, because at some point we need, if we let the master go at full speed in some situations, there's no way the slave can keep up. And if we have a group where more than one members try to write, it's very difficult for them to write effectively if they are not close. But for us, so we had to introduce flow control for this also. But there's also some situations where we want to be able to manage the cluster without Like, for instance, one of the important ones is to add a new member to a cluster that's writing fast. So we have a lot of write workload there, and we want to be able to get in the cluster. But the work of a node that gets in the cluster is much larger than the node that's just running the cluster, because it has to store what's coming in from the network and also applying what's on the queue already. So for this, we introduced this flow control, which is one thing that works a bit differently. Okay, I'll skip the performance things, the graphs. Okay, so on this side, we wanted to say, okay, it's the writer that decides. We instead of doing like a lot of those send a message or something like that to the server and say I'm delayed or something like that. No, we just send, each node sends to the server one message per second, saying, okay, this is my queue. This is my applier queue, this is my certifier queue, this is the number of transactions I tried to execute in the last period, this is the number of transactions I have successfully applied, and so on. And then everyone that is listening on the network knows the state of all members on that network. And with that, whenever a member wants to write, it cannot write more than the state of that the system can withstand. So if we notice that the slowest member on the last period that has a queue growing beyond a threshold that we set, if that queue is larger than we decided it was the maximum, then that node is delayed, and we check how much it was able to run, and then with that, we simply, okay, so it was able to extend 1,000, let's take 10% for allowing it to get the old transactions, and also try to keep it around this 1,000. And then next second, we do exactly the same. We try to always see if the states change, and then we ramp up if everything is clear, then now we're very fast, and then we ramp up. And then again, we always do this one per second. So it's whenever a writer wants to write, it will check the quota that's available for him as a writer. And that's it. So you won't see any flow control messages other than this stats message going around. Okay? But, okay, flow control also introduces some changes. But actually, disabling flow control does actually, in terms of throughput, does not decrease much. It decreases much if you put low thresholds. If you put very low thresholds, this is designed to have a threshold that's significantly larger than the number of transactions you can run in a second, for instance. So it should be larger than if you handle 10,000 transactions. It should be larger than that. Otherwise, it will be doing more throttling than needed. Okay. So, okay. So that's it. Do I need to finish now? If needed, I can skip. Okay. So as I said before, this is just an artificial benchmark, not to the mean sysbench, which I like a lot. It was great for us in development. So, but let me just show what you can expect in this configuration and with this compared to a synchronous replication. Okay. Of course, you have a loss compared to a synchronous replication. We start where a synchronous replication would just commit, and we start our work there. And of course, we have higher latency. Those are the dots and triangles there. And but the thing is, well, we believe that this is reasonable. We are, of course, trying to improve on this, and this is, we have overhead, but this is something we are. It's great for us that we reach already this point, but we want to make it closer. And of course, this is only for sysbench. Let's see how it behaves on all the real users and workloads. Okay, so, but at least it's good for us to be able to reach this point. There's also the issue of multi-master. So, of course, we do not recommend it immediately, but you can use it. And using it, there's some issue about the scaling with the number of writers. So there's a bit of scaling here, but there's no big scaling from using multiple writers when you have a system that's fast enough. Of course, if you have many reads or only a few writes, and yes, of course, you're exploring the read capacity in each node, and then the write capacity will be enough to have some gain. But, well, that's it. It's something you need to study if it's benefits you or not, or if you can use it. And then we also see the growth from 3 to 9 members, which is something which is also good. There's some effect there on 5 and 7 members, but that's okay. So there's no big drop, and there's no big drop because of what Alfrani said. The XCOM layer, the GCS layer that's built below, has capacity to handle this. So even growing to 9 members, we still are able to handle this well. And this is, well, that's easy, okay? And then there's also another thing that Kenny was saying, that you should not use WANs. No, please, what we wanted to say was that it's not as optimized for WANs as we can do, and we were working on that, but you can use it in WANs perfectly. There's no issue there. But of course, what you are doing, if you put this one node that's with some delay in a 3 group, of course you'll delay, but then you will compensate that by moving the line to the right. So you will reach a throughput that's higher, but with more threads. And the same with the 50 milliseconds, and that also grows a bit more this way. So, and this is also over time the throughput, but this is not sustained throughput as before. This is peak throughput. This is the result on Sysbench, and we see there are small dips there, which Rene already complained about, as put the bug there. This is the garbage collection that sometimes enters and lowers slightly the throughput there. Okay, we'll also improve on that. Well, and that's it. Okay, so right now we are waiting also for some feedback and trying to understand how the workloads behave and if we can indeed take advantage of this. But, no. Okay, so the thing is, and I can explain this, the pipeline that we use on the communication system has a number of slots, and those slots are configured. So having a very large latency will decrease your throughput. It will work perfectly, but then you have to know if you can put enough threads in parallel. So if you can withstand all of that latency there. So fine. But you need to know if your application can really withstand such a large number of threads. Yeah. No, the transaction, one transaction, sorry. In terms of execution, no, if you put enough, if you use more transactions, you'll have more parallelism on the server. Yeah, so. Yeah. No. Okay, any more questions? No, okay.
So you're saying that we are using Paxos, Menches, right? So if I recall correctly, Paxos with for majority, right? So in your graph, when there was one node of 3 that was, it says latency, was it because you were writing to it, or this is because even when, let's say, you write on only one node where the majority is fast enough, it slows down or not?
So that's the things we're actually working on, but the main issue is that we have to write to the network. So for one transaction, that's what happens is we reach majority. If we have 2 nodes locally and 1 remote for one transaction, we execute immediately. There's no more delay there. But the thing is, this works for one transaction. When you add many, then at some point, which is the horizon, then it will start delaying. It will also start delaying if we immediately send large transactions. So if you send small transactions and you send only a few threads, it should be able to have very low latency. But then when you have more, then it will have that added latency. Okay? So yes, it should be as Paxos, and because we use that, we should be able to immediately return, because we have two nodes that are low latency. But right now we can do that only as one case instead of in all situations. That's what we need to fix. Okay. Okay.